Hi everyone! Today we're going to wrap up chapter 20, our last chapter of general chemistry. So we're going to start our last lecture by discussing the discovery of fission, and then we'll talk about the atomic bomb and nuclear power. So in the mid-1930s, an Italian physicist named Enrico Fermi attempted to synthesize a new element by bombarding uranium with neutrons. So the idea there is that by bombarding a neutron into uranium, seen below, we would get a new isotope of uranium, uranium-239. And then it was thought that maybe uranium-239 would then go through beta decay and produce a new element. However, Fermi didn't actually analyze his products, so he didn't really know if it actually worked. This was just a hypothesis. So 3 researchers in Germany repeated Fermi's experiments and then analyzed the products, and they found that the products were actually lighter than uranium. They weren't, the same atom with a higher mass. They actually ended up with 2 different elements that had smaller masses. So actually off on the left is a picture of, I think her name's Lisa Meitner, if I'm pronouncing that correctly, and she was one of the scientists who worked on this project. So what actually happens when you bombard uranium with a neutron is it essentially splits apart. So you can see here we have uranium-235, and then there's a neutron that's hitting it super fast and with a lot of energy. And that causes uranium to kind of split apart into 2 new elements. So we have barium-140 and krypton-93. Additionally, we get 3 neutrons that come off of those 2 elements. And of course, we get some energy. So the initial isotope in this reaction, uranium-235, constitutes less than 1% of all naturally occurring uranium. Now, uranium-238, which is the most abundant isotope of uranium, does not undergo fission. It's only uranium-235 that goes through this process, at least with uranium atoms. There are other atoms that can do this too. So, uranium-235 has to be enriched in a sample in order for this to occur. Now again, note that there are 3 neutrons in the products, and so those neutrons could go on to bombard other uranium atoms and cause more fission events. So we'll talk about later chain reactions that can occur here. So nuclear fission is when a large nucleus splits into 2 smaller nuclei via reaction with a neutron. Now there's another process called fusion, which is kind of the opposite of fission. In fusion, small nuclei are accelerated towards each other and then smash into each other to make a larger nucleus. And that was more so what Fermi thought was going to happen. But he was proven wrong, or at least his hypothesis was proven wrong. And what actually happened was fission with uranium. But we'll see that fusion is possible as well. So both fission and fusion release enormous amounts of energy and dangerous amounts of energy. You can see off to the right the atomic bomb there. So fusion releases more energy than fission. So fusion in particular can also be very, very dangerous, or is very, very dangerous. So let's talk about the atomic bomb. This was a huge development in nuclear chemistry. And it came about because the US was afraid that Nazi Germany would develop a bomb based on nuclear fission. So they developed the atomic bomb, and it turned out Germany never had developed a nuclear weapon, but the development of the atomic bomb was part of a secret project called the Manhattan Project, if you've heard of that before. So in 1945, the U.S. tested the atomic bomb at a site in New Mexico, and that's what this picture is on the left. And you can see this is highly energetic. There's a lot of smoke and all sorts of stuff happening over there. And we can see kind of a mushroom cloud on the top. So the atomic bomb was never actually used on Germany. It was eventually used on a couple of different cities in Japan during World War II, and the effects were awful. The bombs killed many, many people, and the ethics of that are still questionable. But science, can be good sometimes, and it can also be very, very bad in other times. So earlier, moving on to a slightly less depressing topic, earlier I mentioned fission chain reactions. So remember that in our fission reaction with uranium-235, there were 3 neutrons that were produced. So those neutrons can go on to start other fissions. So you only need a small amount of neutrons to actually start a chain reaction. So we call it a self-amplifying reaction. Now, you do need a minimum amount of fissionable isotopes to start, and that minimum amount is called the critical mass. And so the critical mass is how much uranium-235 we would need in order for a chain reaction to occur. So here we have a picture showing a fission chain reaction, and again, this is essentially what occurs during nuclear or the atomic bomb. So this was what was utilized to create the atomic bomb. But what happens here is you start with uranium-235 and you bombard it with a neutron. And like earlier, we end up with barium-140 and krypton-93. We also have a lot of energy that's given off by that process. And then if you have more uranium-235 present, the 3 neutrons that are produced in that first step will also go on to create more fission processes. And that's going to, again, create more barium and krypton and more neutrons. And so we get more energy for each of these fission events. And it just keeps escalating. So the 3 neutrons from each of those products will go on to create more fission events. So it just creates way too much energy, and that's essentially how you get the atomic bomb. Now, you could also utilize this in nuclear reactors to produce electrical energy for people to use. So there are some good benefits of these types of reactions. We don't always use them for evil. So nuclear power is more often used in Europe and Asia than in the US. Now we do have some nuclear power plants, and we do utilize some nuclear energy. So you can see we're kind of in the middle here. And again, remember, nuclear fission generates enormous amounts of energy, so we can use that to our benefit and generate electricity. So nuclear power makes up about 20% of US electricity, and it makes up about 70% of electricity in other countries. So if you look at Sweden and France on this chart, you'll notice that they're using much more nuclear power per person than the United States. So part of the reason we're not really a fan of nuclear power is, well, we're huge fans of coal and petroleum and all that. But additionally, there are some problems with nuclear power. It can be very dangerous, as we've seen with the atomic bomb. So some advantages of nuclear energy. We use about 50 kilograms of fuel to generate enough electricity for 1 million people using nuclear energy. And nuclear energy doesn't cause air pollution, whereas coal uses about 2 million kilograms of fuel to generate enough electricity for 1 million people. So that's a huge difference here. But additionally, coal burning produces nitrogen dioxide and sulfur oxides, which add to acid rain. And acid rain breaks down a lot of, for instance, if rocks, or statues. It's also just really harmful for the environment. Additionally, coal burning produces carbon dioxide, which adds to the greenhouse effect, or global warming, or climate change, whichever term you use. Now, that being said, nuclear power, again, can have some dangerous consequences. So even though here we said it doesn't cause air pollution, remember, nuclear fission, which is what's used, is highly energetic, which can be highly dangerous. So, there's a lot of debates that go on about the use of nuclear energy. So let's talk about how nuclear power plants work. Nuclear power plants consist of fissionable material, like uranium-235, and that's stored in really long tubes called fuel rods. So between those fuel rods are something called control rods that are made of neutron-absorbing material. So that's either going to be boron or cadmium or a mixture of the two. So the reason we have control rods is to stop nuclear reactions. So for instance, if we have fuel cells that contain a radioactive element that can fission, remember those need neutrons in order to start. So what we can do is alternate those radioactive fuel rods with neutron absorbing rods, control rods, and those will block neutrons from getting to the radioactive elements. So this is a very controlled environment, which is good because remember, fission events produce a lot of energy, which can be dangerous. Okay, so again, those control rods allow for a controlled chain reaction to occur. So then we generate the right amount of heat needed for electricity generation. So this is a better picture of a reactor core where we have our fuel rods, which contain the radioactive element. Radioactive element. And again, it has to be a radioactive element that can go through a fission process because not all radioactive elements do. And then we have our control rods, which we can use to stop the reactions from occurring. And that way we can control how much energy is generated. Now, in this reactor core, we also have cold water constantly moving through the system. And remember, water has a high specific heat capacity. So water can hold on to heat and retain it really, really well. So water's constantly flushed through the system. So it comes in, it's cold, and then it absorbs the heat from the reaction, and it becomes hot water that then leaves the system. Okay. So this is a more detailed diagram of what's going on inside of a nuclear reactor. Let's see. So our control rods, again, are in our reactor core, and the fuel rods, of course, are there as well. So the fuel rods are yellow, and the control rods are shown as black rods there. So again, we can, raise or lower those rods in order to encourage fission reactions or prevent fission reactions. And then water is also flushed through the system so that we can maintain a certain amount of heat. Additionally, there is a separate part to this where we have a turbine that powers the reactor core. So up on the upper right, you can see a nuclear reactor, and of course it's covered in really dense material so that we can try to prevent high energy radiation from escaping if something were to happen. So as I mentioned before, there are problems with nuclear power, unfortunately. So typically what happens with these nuclear reactors, if something does happen, is we have what's called a core meltdown. So usually that involves some sort of loss of the water that's keeping everything cool enough. So if you don't have water flowing through that reactor core, taking heat away, it can get way too hot and melt the core. So this has happened a couple of times, actually a few times, but a couple of good examples, or rather infamous examples, not good examples, is Chernobyl and Fukushima. So in Chernobyl in 1986, they had disabled some safety features, allegedly, to try to see if they could reduce maintenance costs. And that caused the nuclear core to overheat because it ended up, or the system ended up failing and water was no longer running through the reactor core. And off to the right, you can see the effects of that. There's a lot of damage that occurred there. And in fact, they had to evacuate quite a bit of people from that area and relocate them. There's also a TV show all about Chernobyl, which I actually haven't watched yet. It seemed a little too depressing given all the things that are going on in the world right now, so I might wait. maybe next year. And then in Fukushima in 2011, I remember this was a huge deal. I was in school at the time, and there was a magnitude 9 earthquake near Japan, and that caused the cooling system pumps to fail, and so the nuclear cores overheated, and they're still dealing with the aftermath of that 9 years later. So we've talked about how much energy is, or I guess that energy is produced from these nuclear reactions, but where is it actually coming from? So this is kind of similar to previous discussions we've had about bond energy and enthalpy. We also talked about, for instance, ionic crystals, what happens when they form bonds, or when they break apart, etc. So it's kind of a similar concept here. So during nuclear fission, some of the mass of the nucleus is converted into energy. And from Einstein's famous equation, E equals mc squared, energy is equal to the mass times the speed of light squared. So, so again, we can relate mass to energy. And again, some of the mass of the nucleus during nuclear fission is converted into energy. So each mole of uranium-235 that fissions produces about 1.7 times 10 to the 13th joules of energy. That is a lot of energy. So as a comparison, a very exothermic chemical reaction might produce about 10 to the 6 joules per mole of energy. So this is like more than double that. So this is a highly energetic reaction. So when a nucleus forms, some of the mass of the separated nucleons, again, is converted into energy. And then the difference in mass between the separate nucleons and the combined nucleus is called the mass defect. So the energy that is released when the nucleus forms is called the binding energy. And the greater the binding energy per nucleon, the more stable the nucleus. Okay. So the energy that is released, again, is called that binding energy. So that's the energy that was needed to bind those nuclei together. So in your textbook, there's this nice graph showing the binding energy per nucleon versus mass number. So you'll notice we have uranium-235 on the very far right. And we know that that goes through fission to produce barium and krypton. But on the left-hand side, we have much smaller nuclei, so their mass numbers are smaller. And this graph shows us that the binding energies on the right are usually quite large, and then the binding energies on the left, they have a range. So some are quite large, some are quite small. And on the right-hand side, we have isotopes that go through fission. And on the left-hand side, we have isotopes that go through fusion. And we'll talk about fusion more in a bit. Now in the middle here in yellow, we have our most stable nuclides. So you'll notice this occurs kind of right after iron there. So typically we consider iron the cutoff point for fusion, and then anything higher than that or with a greater mass than that will go through fission. So let's talk about fusion. So nuclear fusion, again, is the combination of two elements to produce a heavier element. So it's the combination of lighter nuclei to form a heavier one. So again, on the last chart, we saw that the elements with smaller mass numbers go through fusion. Now, again, remember, fusion also emits a large amount of energy, similar to fission. And this is the energy source of stars, including our sun. So this is a pretty useful reaction. Without the sun, we wouldn't be alive. However, of course, people decided to use this to their advantage, and this fusion reaction is also the basis for hydrogen bombs. So, you know, there's always evil people in the world. Okay, so off to the left, we have a fusion reaction between something called deuterium. So this is a hydrogen atom with a mass number of 2. And normally hydrogen has a mass number of 1. And then we also have that combining with tritium, which is a hydrogen atom with a mass number of 3. So remember, normally hydrogen has a mass number of 1 due to its proton. But if we add a neutron, deuterium results. If we add another neutron, tritium results. So if those two crash into each other, we end up forming helium and a neutron. So we're taking two lighter atoms, smushing them together essentially, and then forming a heavier atom. So that leads us into something called nuclear transmutation. So transmutation is when atoms of one element are transformed into atoms of a different element by a nuclear reaction. Now, in transmutation, reactions involve accelerated high-energy particles smashing into target nuclei. So typically for this type of reaction, we would use a proton, and then we would smash it into a source of atoms of some sort and try to create new atoms, new elements. So this is done in a couple of different ways. One way is involves using a linear accelerator. So in a linear accelerator, we have a proton source, and then we're accelerating that proton through a series of tubes to a target. So that proton is going to accelerate, 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 and then smash into its target there. So down below, we can see a linear accelerator. It's kind of going that way. That's used by Stanford. So it's super, super long. Now, the proton has to keep advancing through this tube. So what they do is they alternate voltage signals to encourage the proton to keep moving forward. And eventually it keeps moving faster and faster and faster, so that it will really hit its target with a lot of energy. And then the other way to perform a transmutation reaction is using what's called a cyclotron. And these are really large circular tubes, essentially. And so a proton source is essentially accelerated in a spiral pattern. And it accelerates and accelerates and accelerates and accelerates until it eventually hits its target. So this is just another method that's used for transmutation. So in the picture off to the right, we can see an actual cyclotron. And let's see, the cyclotron shown there is in Illinois, and it actually contains or includes two cyclotrons in a figure-8 configuration. So again, particles are just accelerated around those circular pathways until they hit their target. All right, so again, there are many different uses for nuclear energy. We can use it for good, we can use it for evil. Sometimes even when we're using nuclear energy for good, it can have negative consequences, like with Chernobyl or Fukushima. And that's partly why the US sort of avoids nuclear power. We did have the 3 Mile Island disaster, if you want to look more into that. However, we are, as as scientists, constantly trying to move forward, create better, safer means of producing electricity. So hopefully we'll find a good use of this energy in the future. But anyway, that's the end of chapter 20. And that is the end of our general chemistry sequence. So you made it all the way through. I know this quarter was tough. We had to do everything online, which is a little strange. And I know there's been a lot going on in the world that has been really tough to deal with. So, good job making it through, especially with all of the emotional stuff going on, the, strenuous mental stuff we had to do this quarter. But if you do have any questions, let me know. And good luck on your final exam. And hopefully I will see you in the fall in the organic chemistry class. So I will see you soon.